let's get going with where we left off last Thursday. We got through most of this scanning and enumeration topic, but I wanted to make sure we didn't kind of gloss over what is really a critical aspect of it. We were focusing on these tools and the underlying protocols to really provide stealthy and effective ways and ways of managing that trade-off between stealthiness and effectiveness, ways of managing and determining what ports are open on a given host, right? First, we can try to determine if a host is up or not. Is it even responding to anything? And from that, can we then later determine what ports are potentially open, closed, or filtered on that device? We can go further than that. And I think it's necessary as part of this scanning and this enumeration phase to go further than that and attempt to make what I think it's fair to call educated guesses of what operating systems, what services, as well as what versions of services are running on those particular hosts. Some of that just comes from what we're calling educated guesses, or call them statistical inferences if you want, which is just, for example, if ports 139 and 445 are open, you're very likely to be connecting to a machine that's running some version of Windows. Now, you can always retort and say, well, Joe, maybe that's not the case. Maybe this is a completely different machine that just so happens to be running port 445, and it has nothing to do with file sharing in a Windows system. It just so happens to be a totally different machine running something on port 445. And that could very well be the case. But so when I say making an educated guess, at this stage, that's all we're really talking about. You see those ports open, there's a statistical likelihood that that is what you're seeing. It's not any way, shape, or form a guarantee, but it's a trail, right? It's another breadcrumb that we're following along to try to understand the system as a whole. Likewise, for your commonly open Linux ports, you have a reason to believe that that's what the underlying system is. You don't have a guarantee of that, but it's a good next step to take here. You can also, and Nmap is an example of a tool that takes advantage of that, look at what is in practice different implementations from one vendor's IP stack and another. We talked about this a little bit on Thursday, that you have this specification. Here is what a TCP IP packet should look like and in what ways it should be used. That's a very long specification. It is hundreds of pages long. And you have these different, all fully compliant implementations of those specifications. And this isn't just IP, this could be from application layer all the way on down. And there'll be just some nuances, some subtle differences in implementation. They're not all sharing the same code base. They're implemented by different groups, potentially targeting different classes of hardware, and consequently, there will be some subtle differences in terms of what those packets would look like at a relatively low level. Here we're talking about which flags are set in which circumstances, what other fields have certain various default values, and there's just some subtle differences between that. So as part of that probing process in which we're determining which ports are open, Nmap and other tools can also attempt to make a guess as to what operating system is running, based on just looking at the low-level traffic itself. We want to go further than that. I mean, the whole point of understanding the overall network posture is to then next determine the security posture of the underlying systems here. You can start to dig deeper to determine not just what operating system is running with what ports it has open, with what our best guess of what services are running. It's next then appropriate to determine potentially what version of those particular services are running. We did a little bit of that with banner grabbing, but only certain services are actually going to be outputting banners that one could grab. But effectively, an equivalent can be done at the port scanning level of determining, based on the particular patterns that a given service is providing, we can figure out certain things about what version of both the operating system that it's running under, as well as what version of the protocol or application is actually providing that particular traffic. So when we talk about the somewhat not interesting distinction between scanning and enumeration, some of our resources we're looking at will differentiate enumeration as this kind of further, deeper digging of probing. From a dictionary connotation perspective, enumeration just means kind of counting, kind of taking an account of things more carefully, and that's what we're doing here. We know what machines are up, we know what ports potentially they have open, we now may know what operating system is on the machine, and for certain ports, certain services, certain combinations of therein, we may then know what versions are running on there. And from there, as we kind of jump into our next task here, we can certainly look at vulnerabilities and potential exploits as well. And that's what that -SV flag would provide for you. Give me the version, service versions here. And then there's also kind of the default -A for just aggressive scanning mode. I do want you to remember that there's a reason we don't necessarily do a heavily aggressive scan at all times. In our classroom environment, in our virtualized lab infrastructure, it is not that big of a deal. But in practice, we always have to be a little bit careful between the effectiveness of our scan, the aggressiveness of our scan, and the potential stealthiness of our scan. That if you're okay with the other side determining that you've performed a scan, then feel free to be as aggressive as you'd like. But there's different things we can explore in a more subtle way if we're more interested in still discovering the information we need to discover, but not necessarily flooding the firewall and IDS with the kind of traffic that Nmap and corresponding tools would be generating. Finally, I wanted to talk a little bit about the Nmap scripting engine that comes up in Lab 2. This is one of the parts that was not working entirely as expected, depending on when you did this in the lab. The idea is that it allows some of these commonly occurring tasks to be automated. Now, that in itself isn't that interesting, but I think what's more interesting is sort of the community and culture that has kind of been built up over a period of years around building and submitting scripts for Nmap through the Nmap scripting engine. Um, it allows for doing more complex things than what just kind of a default scan would provide for you. It is as it sounds. It is a way of automating different aspects of Nmap's built-in capabilities. Sometimes also it's not just doing complex queries to determine things like versions. Sometimes also there's either detections or actual capabilities of providing exploits in the scripts themselves. That's not really its intention, so it's not meant to be an exploit engine itself, but it could in fact be used for that purpose. Um, I've also seen some stories regarding different security agencies providing their own series of scripts. If there's a concern that there's a particular vulnerability, by providing a script to check if you're vulnerable, that's one way to ensure that you potentially patch that particular script. Here's two historical examples. There's another one that you explore in the lab. One that checks whether Nmap checks whether or not there's FTP available and whether anonymous logins are enabled. And there's another one to detect if the Apache Struts remote code execution is vulnerable on that machine. That was the big Equifax issue. This is, let's zoom in a little bit here. This is the FTP, anonymous FTP script here. This is, in a sense, a domain-specific language specifically for scripting Nmap, but this is actually a well-known programming language. Can anyone tell what that is just by seeing things like local, what's another keyword? Local function. Close, actually not too far, it's not quite SQL-ish. Um, Oftentimes, if you have a tool and you want to embed a custom language within it, the most common thing, at least historically that's been used, is Lua. So it's very nice to see Lua in this context here. And that's all this code is. People like using Lua in C and C++ projects because it's very easy to embed into those larger projects. So you have this more complex C++ application, as is the case here. You want to embed a little kind of custom language to script and automate some things. Lua is a very common choice for that, at least in the systems engineering field. And we can kind of, as we've done for other programming examples for which you're not necessarily required to be an expert programmer in this course, we can still kind of squint our eyes at it and get a feel broadly for what it is doing. I'd have to scroll down, I think, a little bit on this one, some sort of input processing. And then I think we can try to figure it out. There's some FTP engine already provided as part of Nmap. Try to connect via it, and then can we do it via some anonymous login, and can we get like a listing of files in a directory? So it's as the name implies, through Nmap, attempt to connect to this port for FTP, determine if it allows anonymous login, anonymous listing of files via FTP. Whether or not that's a vulnerability depends on your scenario, but as a default, it's maybe not a great default to have. The other example here is looking for that particular vulnerability. This is a little bit more cut and dried. We'll talk more about CVEs and this particular CVE here. And it's specifically looking, there's a lot of documentation here. It's specifically looking whether or not this particular request is going to work or not on the site in question. And if it is, that's a problem because that means that it's vulnerable to a particular remote code execution vulnerability. This example does not exploit the vulnerability. Instead, it's just checking if that request passes true, if it doesn't get blocked, if it doesn't fail, then the system is otherwise vulnerable. That's a useful piece of information to have. You do something kind of similar in Lab 2 where you do an Nmap script to detect if there's an SMB vulnerability, assuming that machine is still running. And then in Lab 3, we go to the next step, which is, okay, what would it take to actually exploit that in practice? And I want to kind of just jump and switch gears directly into that. So that was kind of finishing up our lab or lecture 3 content and just directly connecting it to our next content here, which is maybe not super great name of system hacking. That doesn't really mean anything. I mean, this whole class is system hacking. This whole class is ethical hacking methodology. So as a separate name for a lecture, it's not super great or super meaningful. Probably a better name for this lecture would have been like, gaining access to a system or detecting and exploiting vulnerabilities. I think would have been an appropriate name for this. This is also the name that the book that we rely on is using for this particular topic, so we didn't just make it up. But really, that's what this week's topic is about. So we've done our scanning and enumeration. We know a lot, hopefully, about a machine or network that we're interested in. Can we actually then gain access to the system? For this class, we are going to focus entirely on using existing vulnerabilities and exploit databases versus crafting our own. It's a different skill set. To create your own vulnerability for a piece of software requires a fairly deep understanding of that particular piece of software or class of software. And that's not necessarily something that would be expected of you in an undergraduate cybersecurity either course or really curriculum. So that's just detecting vulnerabilities in and of itself. Not even to mention actually crafting of exploits, which then usually requires both that knowledge of vulnerabilities, which pretty deep understanding of a particular class of software, but then crafting exploits then requires even deeper sort of understanding of OS security models, underlying low-level system software, and the like. And so I think for our learning outcomes of this course, and really for cybersecurity certification and degrees here at the undergraduate level here at Iowa State, I think it's sufficient to gain an appreciation for the types of vulnerabilities and exploits that are out there. And as a practitioner in the field, that's likely also going to be sufficient for you. That determining whether something is vulnerable to existing exploits is sufficient work that one doesn't need to, unless that becomes your passion where you want to go into, need to be in the business of creating, finding your own vulnerabilities and exploits. Now, that can also be a lucrative career. The people who can do that tend to focus on particular classes of vulnerabilities. So it's not the same people looking at web cross-site scripting vulnerabilities are not the same one looking at really low-level network handling vulnerabilities. And frankly, again, there's enough that we can examine and gain an appreciation for by just looking at existing ones. We won't be writing our own, but I think it's important for you to be able to look at a vulnerability/exploit combination. And again, at that same kind of hand-wavy level we've been getting away with all semester so far, being able to gain knowledge of the broad strokes of what it's doing and why it works. It shouldn't look like complete mystery to you when we look at one of these examples or multiple of these examples. That doesn't mean you'd be expected to have the skill set to do it yourself, at least as of yet. Certainly for a learning outcome of this class, that's not expected. It also tends to be very operating system dependent, so we'll look at Windows and Linux-based approaches somewhat separately, and that's what you'll be doing with your virtual network starting today in lab. But from that perspective, it may not feel that much different than scanning and enumeration to you, because it's a very similar kind of class of investigation that we're doing when we're actually doing the exploit. So in lab 2, or previous topic, we're determining what the hosts are, and broadly speaking, what are they running? And now this next task is effectively just correlating that lab 2 or lecture 3 knowledge with this material, which is what is available to currently, how is it currently vulnerable, and what kind of exploits are available. That is, again, different than saying, here's what's running on a system. Can I myself determine new vulnerabilities and craft new exploits for it? That would be a pretty big lift for us. Instead, gaining awareness of what's out there is I think, sufficient. And when new vulnerabilities come out, and that happens quite frequently, when new exploits are in the wild, having an appreciation for, broadly speaking, what they are attempting to do, I think is sufficient for your purposes. There are these other agencies, other organizations whose main purpose of existing is to let you know how serious a particular vulnerability or exploit is. But you yourself, given your cybersecurity knowledge gaining here and later in your careers, will also be able to form your own opinion about the relative seriousness of something. You won't just have to blindly follow what others are telling you. You'll be able to appreciate existing vulnerabilities, existing published exploits, and determine to what extent that is a big problem, little problem, medium problem for you here. But that's what we're doing. We're finding and applying existing exploits. If the scanning and enumeration phase was already considered an active phase of the attack, you may argue, well, we're just sending network packets and reading responses. We do that all the time. What makes that active? That's still considered active because you're directly engaging with the underlying systems you're interested in. But now there's really no ambiguity in the fact that we're sort of in an aggressively active phase of the attack. Now we've learned about whatever that particular machine is running, what it's doing, and we're determining, based on what we've learned, is it vulnerable? Can we actually exploit it? Or alternately, could it be exploited by someone? This has a bit of a challenge with regards to categorization, right? There's so many different things that are potentially vulnerable. This wide space, from operating system to network to web applications, or even some of the physical vulnerabilities we'll be talking about later. There was perceived a need to have a common set of frameworks to categorize them, to focus both on the underlying weakness as well as the severity and impact of the resulting vulnerability here. Now, there's going to be a little bit of alphabet soup here, and I don't think your goal today is to make sure you have that all memorized. Some of this you may already be familiar with because we're abutting it sort of all semester long, and we'll continue to do so. This is something that maybe is a lead for you to explore a little bit further kind of on your own here. But we'll start with this concept of the common vulnerabilities and exposure list, or just the CVE list, or they're just referred to CVEs as themselves. The CVE is a publicly disclosed vulnerability and exposure. We'll talk about what that means. There's also the National Vulnerability Database, which is sort of directly correlated and synchronized with the CVE list. That gives a little bit more information than what the CVE list itself provides. Things like the severity score, things like an attempt to kind of relate it to what particular actions an attacker would have to take to exploit that vulnerability. But even though it does contain different information, when someone says there's a CVE, it's going to be located in one of many different types of databases, and they're all going to be directly linked to each other. So just thinking of things in terms of CVE and what CVE number is applied and the information about it is probably sufficient for our purposes. You can learn a lot just by perusing vulnerability databases. It is a little bit of a fire hose of information. There's a lot of software in the world, and there's a lot of vulnerable software in the world. So I would say it's not as easy as just kind of starting with what's the most recent CVE and working backwards, or what's the oldest CVE and working forward. There's just far too many of them for you to be able to do that. But you can learn a lot by perusing those databases, by picking a piece of software that's relevant to you and just gaining an understanding of either what current vulnerabilities are perceived to be out there or what historical ones have been discovered in the past, and just trying to dig into them and figure out what did this vulnerability mean, to what extent was it severe, to what kind of extent was it actually exploited in practice. I just picked a couple of examples here. I was thinking just about this course, what software are we using in this course, and just said, well, we use Canvas, at least to some small extent we use Canvas. Canvas has lots of CVEs. Canvas is not a well-written piece of software, and so it's not surprising that there's lots of vulnerabilities associated with it. We can click on one of those and take a look at one of those just to get a feel for what that looks like in practice. That's cve.org. That's the NVD page from the National Institute of Standards and Technology. Here's CVE 2021-3659. Sounds bad to me. We'll talk a little bit more about the remainder of that kind of alphabet soup of information here. But at the very least, you can take a look at it and get a feel for, okay, this was 2021, ancient history, but Instructure, it's the name of the company, Canvas Learning Management System, didn't properly deny access to locked, unpublished files when the unprivileged user accesses the doc viewer-based file preview URL. To me, that seems like a really bad vulnerability. Well, to the extent that anything we do here is that critical. I've uploaded a file, exam1solutions.pdf. I unclick that students can access it. If you happen to know what URL that was located at, looks like to me that you were able to access that file anyway. To me, that seems like a pretty big deal. This was one for Discord, and Discord's a piece of software that's attempting, to do a lot of things and to be a lot of things for a lot of different people. So it's probably going to have all the vulnerabilities that any web rendering engine is going to have, any script processing engine is going to have. It's going to have a lot of vulnerabilities associated with it. Issue for Discord for Mac OS version, I don't know how old that version is, 0.0.291, allows remote attackers to execute arbitrary code via blah, 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 via some JavaScript processing engine associated with Discord. That also seems very bad to me as well. So you're running Discord, you're just trying to get updates in class, and all of a sudden someone is executing arbitrary remote code on your system. We usually want to avoid doing that. These were both examples of CVEs in that NVD database, and we will talk a little bit more about what some of this other information corresponds to. Again, today our goal isn't to necessarily have all this memorized and become experts in it. There's some sort of pointers I'm providing here. I would want you to review this kind of offline and get a better feel for some of the detail that we're kind of just presenting a first glance at here today. This is another example, and this is Rapid7's database, and Rapid7 is pushing some software products that we'll talk about a little bit later this semester, but it just is another database that provides a little bit more of details of these particular vulnerabilities. We've also looked at ExploitDB before when we were looking at the listing of Google hacks. Really, the original design of this database was to also be Tenable's listing of vulnerabilities, CVEs, as well as for many of these, the actual proof of concepts for those vulnerabilities. Now, we talk about exploits, and that can actually mean a couple different things depending on the context. Oftentimes, so we talk about a piece of software that has a vulnerability. It is doing something wrong, like for example, it is not locking a file properly when the instructor thinks the file is locked. To exploit that vulnerability could mean a couple of different things. Most of the examples in this particular database are just there to show whether or not a particular system is in fact vulnerable. So they're proof of concept in the sense that they are kind of a green flag, red flag kind of result that says, yes, you are vulnerable, no, you're not vulnerable. A very useful thing to have, like we saw in that Nmap scripting engine providing that functionality. But for some of these, and these are also some user-provided scripts as well, it's in fact going that step further, which for the Canvas example, it's harder to go much further than that, but for the Discord example would be a proof of concept that would actually show that if you were to deploy this particular code in your particular Discord server, you'd be able to show remote code execution on the user's machine. Even from that perspective, you could still go a step further and have a proof of concept that then not only detects if the software is vulnerable, provides an exploit that shows the vulnerability in practice, and then maybe then does something malicious on top of that. These examples tend not to go to that extreme. To the extent they do anything malicious on the resulting system, they will attempt to bring up a remote shell, which is sufficient, right? Once you have a remote shell on a system, you can do all sorts of fun things after that point. But they're not things that are going to actively delete all your files or do things that would be truly malicious. They're still ultimately really for just proof of concept in the resulting machine. You have to go elsewhere if you actually want to do malicious things. So more about CVEs. It's the Mitra Corporation that has funding to operate the CVE system, and they're the primary agency that assigns those CVE numbers. The term CVE identifier or CVE numbers, or sometimes just the word CVE is kind of synonymous with the number and the identifier. They are the primary CVE numbering authority But as you will see, other major software manufacturers have their own authority to also assign their own CVs for their own products. Also, companies whose job is to discover these vulnerabilities also have the ability to assign their or request and assign CVEs for those vulnerabilities. These are all sort of stored together ultimately in the same global databases here. Um, Beyond just the basic technical description that we just kind of reviewed for a couple of those examples, we'll talk about this as well, that CVEs also provide a link to the common weakness evaluation, that's the CWE, that underlies the vulnerability. It's an attempt to answer, with not really going into a ton of technical detail yet, why is this a vulnerability? It's one thing to say the what of the vulnerability, that's the CVE. The CWE is an attempt to answer, again, at a pretty high level still, why is there a particular vulnerability? And then there's an attempt to also provide some sort of quantifiable score associated with that vulnerability. That's the CVSS. Two other things that Mitra also manages that we'll talk about on Thursday is the common attack pattern enumeration and classification, the KPAC, as well as the attack matrix. Different way of also just categorizing hacker methodology, hacker process. We'll bring those up, we'll mention those. It's important to claim we covered those in this class. We're kind of discussing our own version of the same exact methodology in this class, and so we don't really have to start with those and have those be primary in this particular class. And despite all the alphabet soup that you'll eventually be kind of remembering, Mitra itself is not an acronym, just FYI. This is something that Mitra also publishes, kind of the historical trends of CVEs. So I thought you may find this kind of interesting, and you can directly click on that link as well. The color coding is a little bit ambiguous because it's kind of a relative on a column by column basis here. So you can't necessarily look at the color coding and say darker red is worse than lighter red here, but it's just the relative trends. It looks kind of purple on the screen, in fact, but it's red and pink on my slide here. And it's important to mention, you may hear in other classes that, oh, buffer overflow vulnerabilities aren't relevant anymore. Well, relevant is a relative term. In terms of CVEs in the year 2024, some aspect of, I would put these as like low-level memory issues, both memory corruption and buffer overflows or heap overflows are still a thing, right? In CVEs, that's in several thousand that have occurred just in the last year alone that have to do with that kind of low-level programming mistake that people claim, well, just write everything in Rust and you won't have that anymore. Well, people are still writing lots of memory unsafe code, and we're still finding these vulnerabilities over a period of years. The other thing I guess you could say that is definitely not a solved problem is all the different flavors and the other alphabet soup of kind of web vulnerabilities or web infrastructure vulnerabilities. That's your cross-site scripting. That's also your SQL injection. That's your cross-side and server-side request forging. That's your XML request forging. They're all very kind of similar concepts of what they're doing. Now, those are still kind of not a solved problem. It's also the prevalence of that class of applications are so critical, it's worth later on in the semester spending time specifically on that category of vulnerabilities, separate from just a broader understanding of vulnerabilities in general here. So the CWEs is a list of the common weaknesses. What is generally wrong with software? It also includes some hardware aspects as well, and the general mitigations. The mitigations are never easy fixes. It's the old joke, the guy goes to his doctor and says, it hurts when I do this, and the doctor says, then don't do that. It's kind of that issue with these CWEs, which is they are a symptom, not a cause, in the sense that it's due to various programming practices that have been followed for generations now that tend to result in these categories of weaknesses, as well as just broader, harder to solve system design problems that there's no magic wand to kind of fix those. There's about 1,000 different common weaknesses, but they're broken into 3 different kinds of top level categories. That's sort of the conceptual weaknesses here. We won't talk about a lot of those this semester. We'll focus primarily on sort of software development weaknesses. And then there are separate sort of hardware weaknesses as well that are kind of interesting. Here's an example of what a CWE looks like. This actually isn't a CWE listing, but we can bring that open as well. This is a visualization as well as an intentionally kind of trivialized proof of concept. So what you get just a good feel for when I refer to something as being related to a particular CWE, this is what one of them could look like. This is the so-called use after free CWE. Has anyone heard about a use after free bug before? It's okay if maybe a couple partial head shakes here. Um, it's one of those things that as a programmer, when you look at these intentionally kind of trivialized proof of concepts, you'll say to yourself, well, I would never do this as a programmer. But in practice, with fairly complicated and certainly complicated multi-threaded software, um, it happens over and over and over again. So it must not be an easy thing to avoid doing, at least when writing low-level memory management code of the kind that some of you have been taught to program in here in electrical and computer engineering. You've probably written some code that has use after free errors in it, but you're not writing code that's being used in publicly accessible web services and the like, and so no one's probably cared or looked at your use after free errors. We can briefly walk through what that code is doing. Again, these examples you would see in a CWE listing are meant to be maybe as few of lines of code as possible, and so they're meant to be kind of silly or trivial in that sense. But in practice, in this case, we have a use, and then we have a freeing, and unfortunately the use is happening after the freeing. It may not be 3 lines of code apart. It could be in a completely separate module, separate file, and 5 minutes apart. We don't even know in terms of temporally or in terms of lines of code how far apart it could be here. We have a structure that gets dynamic, that has a pointer assigned to it here. For a pointer to that structure, we're just allocating a random integer here. And if this is completely foreign to you, that's okay. You're not going to get tested on whether or not you can look at low-level C code and appreciate vulnerabilities or not. But for those of you who have seen this before, this is my attempt to kind of walk through what's happening on this slide here. Malloc is doing our dynamic memory allocation. That would correspond to number 1 in that slide above here. We want an integer. Why are we allocating one single integer dynamically? Because this example is meant to be as simple as possible. We want one particular integer. We then do something with that location in memory. In this case, we've just assigned it to 0. Could be all sorts of things we want to do with it, but eventually perhaps we assign it to 0, and we also then free that dynamically allocated region of memory. So we have a region of memory, it's dynamically allocated, it's freed, and then as a programmer, we tend to think of that memory as now being gone. It's removed, it's freed. You're free now, memory, run through the fields, but it's still there, right? It's ultimately a very physical thing, right? So freeing is sort of an operating system bookkeeping operation, right? It's that particular address is now free. It's now available for the operating system to then put something else in there at that place. And there's all sorts of fairly complex algorithms for how an operating system manages dynamic memory and where it puts things, but there's certainly no guarantee that the very next thing you choose to allocate, which in this case is this other structure, there's no guarantee of where it's going to go necessarily if you're relying on the operating system to do that allocation for you. So there's certainly a possibility that as you've already freed something and now you've allocated something else, that it's going to get put in the same exact location. So step 1 is the malloc call. Step 2 is the free. Step 3 is then that second malloc call there. And the idea is that in part or in whole, there's some overlap between those address ranges that are provided here. So far, this is all still fine. This is common programming practice. Again, the code is not doing anything particularly interesting, but there's nothing wrong with the code. The actual use after free error is on this particular line here, which is we had a pointer, we allocated something, we dealt with it, we then freed it, and then later on in the code, we tried to use that pointer again. And what happened here? Well, and again, this is meant to be trivial. We checked if there's something non-zero at that pointer location, then run a shell script, or run a shell, execute a shell. That's not likely to actually be in your code, but if you can have a use after free error, lots of things are potentially possible. This is kind of a absolute synthetically worst case scenario for you here. And you may look at that and say, That will never happen to me, right? I've written a free. I'm never going to put this line of code 2 lines after the free. Well, it doesn't have to be 2 lines. It could be several minutes later. It could be several files over. You could be passing these pointers through all sorts of different functions. And it does turn out that in practice, while it's kind of just combined into this general memory corruption kind of basket here, amongst other things as well. So I don't want to make too much of a strong claim here. In publicly well-tested, well-reviewed software, it still happens many hundreds of times in a given year amongst people who get paid a lot of money to write that software, or open source software that's reviewed by lots and lots of people before it gets pushed out. That kind of thing, that kind of CWE, which is a very common one, still happens on a very frequent basis. In 2023, they provide the sort of top 10 known exploited vulnerabilities, and that word known is doing a lot of work here. There's known knowns and known unknowns, and then there's unknown unknowns, right? When we talk about these CVEs and the corresponding CWEs, this is what has been detected and published. I think it's fair to assume that that should broadly map to the trends of what is actually truly vulnerable, but ultimately, these are the things that get published oftentimes many months after the fact of which they've actually been patched. So you don't necessarily have an exact snapshot of today, what the world looks like from a software vulnerability perspective, but you have the broad strokes of the greater trends of what's happening here. And we can see in terms of this top 10, which is being ranked across a couple of different criteria here, that number 1 is still use after free. Number 2 is heap-based buffer overflow. This one may not have a pretty picture here. Buffer overflows generally lead to crashes, but other bad things can happen when there's a buffer overflow. And this is probably the simplest example they could come up with here. This is something that you've probably done yourself if you've ever written C code, but you've done it accidentally and you've determined that it happened because your code probably crashed. And that's how you knew you probably had an out-of-range memory access. If you've ever written a piece of C code and gotten a seg fault, has anyone gotten a seg fault on a piece of code before? If you've written C code and not gotten a seg fault, I don't believe you, and that's okay. But not all of us have done C code, and that's fine. But it's such a common thing that now tooling has gotten a lot better at telling you when it's really obvious that you've done these things. But there's nothing in the language specification itself that prohibits you from doing this kind of thing, which in this case is, I am processing input arguments. I have yet another pointer here. I'm doing a dynamic memory allocation of 256 bytes to store some information. And I'm copying the first string that the user passes to this program into that buffer. Well, what's wrong with that line? Those of you who've seen it before, again, I don't expect everyone to have seen this before. What's the issue with that line? Sure. And there's actually very few limits. There's some OS dependent limits on how long that argv of one string could be, but it could be very long indeed. So what winds up happening in your C program, this function, which we're not supposed to use anymore, copies starting from this first location to this first location, copies until when? When does it stop copying? Does anyone remember? When what? How does it know when it's done? This is one of those C implementation details. When it gets a null, right? When it sees a 0. And if it's random garbage data, I guess eventually would see a 0. But otherwise, it's not going to stop at all. And it's not going to stop at all at 256. This function, for better or for worse, and this function is much older than everybody in the room here, myself included, has no way of knowing about length. It just keeps copying until it hits a 0. That, in fact, is a big issue. And if your counter argument is we just should not be writing code that looks like this anymore, you are probably right. You have to convince some much more powerful people than me of that point to have your way. We can look at a couple of other of these as well. It's an interesting combination of what I would call, for want of a better word, really low-level C programming bugs, as well as much high-level kind of system design issues with regards to how we write web resident software. I think the nice thing about our lab infrastructure is that over a period of the next few weeks, as you're doing these kind of point-and-click type of labs, you're going to effectively try a few different versions of each of these to get a better feel for them. For the web one specifically, we'll have a separate topic where we talk just about those. They're important enough, they're easy enough to exploit that one should really have separate understanding of what's happening there. But those are your CWEs. That is related to a particular CVE, and it'll say, for example, for buffer overflows, I believe this is for that particular year, there were 32 heap-based buffer overflows that were CVEs, and they had an average severity score of 8.79, which it's not a linear scale, it's not an exponential scale, but higher is worse, I think, is a sufficient takeaway from your severity scores here. And we can talk a little bit about that. That's your CVSS, that's the industry standard for assessing the severity of vulnerabilities. It can help you as you're detecting what systems you're responsible for that are vulnerable to various things, of how vulnerable they really are. I think you still need to have particular domain knowledge. You still need to have an understanding of what this particular vulnerability looks like in practice, because it's really hard to say, well, this vulnerability is an 8.7, I need to prioritize this one over an 8.6. That scale doesn't work that way. It's essentially just a spreadsheet, and I want you to be aware of that, and I want to actually just show you the spreadsheet for what CVSS looks like in practice. Our projector looked better last week. This is a web tool, but it could very easily just be a spreadsheet to kind of calculate the final number here. So for a vulnerability, as one discovers and publicizes that particular vulnerability, whether it's the software manufacturer themselves, whether it's a third party, whether it's Mitra who's making the final decisions here, there is basically a series of categorization questions that are then answered about it. And sometimes these things can be kind of argumentative and almost sort of political in nature, because as you'll see for some of these categories, people can disagree about what the actual answer should be for these. So anyway, you have these various base metrics as well as system impact metrics. So for example, if we had a vulnerability in which I needed to have local access to the system already, and that means I'm already a valid user on the system, and I'm probably going to increase my privileges on that particular system. And the attack complexity is high. Again, low or high, at some point that's a binary decision. People have to agree on what that means, and that's a negotiation more than just a scientific fact, whether something is low complexity versus high complexity. Privileges just require low privileges and can be done with passive user interaction, so nobody has to click on something. Now for our CIA triad, how much of that is being impacted here? My data is getting leaked, it's getting modified, and the whole system's getting shut down. And for subsequent systems as well. And then there's some supplemental here, things that I don't think change the score any. So as you saw, as I was clicking things, it was changing a couple things here. It was changing that very long and intended to be human readable, but in practice, I think you have to go to a decoding website, that string that indicates essentially just the answers to all of those questions. And I think the easiest way to see that happening is just to click on maybe the first thing here, attack vector. This is CVSS version 4.0, and there's prior versions as well, but everyone uses 4.0 now. The first thing there is AV:L, and that literally means attack vector is local. If instead it could be done over the network, then what changed in that string was just it went from AVL to AVN. So you could start to interpret that string as human readable, unless I think this was your day-to-day job. It's much more likely you probably go back to this website and review what it tells you about what the string corresponds to. And the CVE listing itself will include a link to this website for you to be able to decode it. If we go back to Canvas LVM, this is old now, this is using version 3.1, and you'll be able to click that link and it'll give you the listing of what all of those things mean for that particular thing. So I'm not suggesting you have to memorize those particular kind of string that gets generated here, but that's exactly what that corresponds to. It is what are the answers to these exact questions in order. That is your CVSS string. And then there's also then your calculated CVSS score, which is why I'm referring to that as a spreadsheet. The specification is provided here. It's not written in that user-friendly of a manner, but we could reverse engineer it as well. As we go from the same exact attack otherwise, and not all else can always be equal, from something that requires physical access, meaning I have to be able to plug in something generally or type something locally, right? I need to be physically there. And we'll talk about how that is an important consideration, but for today it's not as important. Two, I need to have legitimate access to the system. So I need to physically be there. I need to have local legitimate access. I need to be kind of adjacent to the system, or I can do it just remotely over the network. What else changed? Not just that string, but also the perceived severity of the score changed from quite a bit, right? From a 7.3 to an 8.9 on this sort of 10-point scale here. Other things would change corresponding string entry as well as the resulting severity. Again, whether something is low or high complexity um, is an opinion. What is low, what is high, right? Basically, it's a way to try to provide this binary decision of how much effort would an attacker need to make to be able to actually exploit this vulnerability. Well, what is low? What is high? How much is your time worth, right? That's not an easy question to answer. It's really vulnerability dependent. But we can see it can make a massive difference in terms of the resulting score. With the general feel amongst people who are active in this field, that once you get to 9.0 and above, you must find a patch immediately. That is now a red, a siren going off, and then one has to deal with that immediately versus anything as it gets into the eights and starting to the sevens, it's less critical of an issue. Now, this is more my opinion on it, and this is just meant to be a little bit funny. Okay, if you have a piece of software and it only has a 6.4, does that mean we don't care about it? Again, it's a lot of what we do here is more of an art than a science, right? So something was discovered to be vulnerable. What that score is attempting to capture is some method of quantifying whether it's going to be actively exploited or could be actively exploited in your given systems. But that is not to say that a 9.8 absolutely could be and a 6.4 absolutely couldn't be. It's the relative likelihood or the relative effort or the amount of sleep you should be losing about that particular vulnerability. But it's not binary at the end of the day. If someone is able to take advantage of this vulnerability, it didn't matter if it was a 6.4 or not. But you will see that as a various vulnerabilities discovered in, say, the Linux kernel, there will be a lot of negotiating about what that actual score should be. Because if it's a 9.0, certain distributions have to actually take action right away and backport a fix. But if it's a 7.0, they're not required to do that. They just have to provide an optional fix available for it. So while it's not a binary thing, while we have to be a little bit careful about making this rank order of severity of a vulnerability, people do actually care quite a bit about the resulting CVSS score. And from our purposes, I think a valid learning outcome is being aware that ultimately, while it's just a spreadsheet, it's an influential spreadsheet, and that long kind of string you're seeing there is literally just the answer to the following spreadsheet questions, no more, no less, and the score is calculated based off that. Let's leave things here for today. Don't forget our quiz on Thursday, and we'll just kind of continue on this topic.